Hello, everyone. Welcome back to the industry track. I hope you enjoyed a break and some good networking out on the main stage. I'd like to get us kicked off for our next session with a very important speaker. I'd like to introduce to you Dr. Melissa Orme. She's the Vice President of Boeing Additive Manufacturing. So I'm going to bring her up on the stage right now. Melissa is going to be talking to us about recent advancements at Boeing related to additive manufacturing.
Okay, can you see me and hear me okay?
Yes, we can. Go ahead.
Awesome. Okay, so I will share my screen, my presentation, and get started. Let's see. Probably would be good to start at the beginning. Okay, so can you see that okay? Was I successful?
Yes, it looks great.
Awesome. Okay, so yeah, thank you for the really nice introduction, and it feels great to be here in this conference with so many, talented and strong women in additive manufacturing. So, I really appreciate the opportunity to be here. So, a little bit about myself. I began my career in academia. I basically rose to full professor from, assistant associate full, and my research program was focused on what we now call additive manufacturing. At the time, we called it solid freeform fabrication or net form manufacturing. Later, I transitioned to the CTO of Morph 3D, which is a small startup which is focused on additive manufacturing to the aerospace industry of flight hardware. And so in that capacity, we really led the created the fixed process, got it, prepared for AS9100 certification and that sort of thing. And a few years into that, I was recruited by Boeing to join the company, their team, and to lead the additive manufacturing activities across the enterprise. That was been about 18 months ago. So I'm the vice president of Boeing Additive Manufacturing. We're focused on metal and flyaway parts for tooling, and connecting our value stream to its digital thread so that we can optimize and drive towards scale and increase quality. So I'd like to tell you a little bit more about our additive manufacturing capabilities at Boeing. So we have 20 sites worldwide. They're in the United States, Canada, Australia, and the United Kingdom. The map there shows our United States centers. And our focus areas, we are primarily focused in flyaway metal and polymer parts, as well as legal tooling and production aids. And these are really factory and engineering aids, such as ergonomic enhancements for the factory floor, or wind tunnel mock-ups, or development prototypes. We're strongly focused on implementing model-based engineering and creating the digital thread along every single step of that value chain, and using that connected data in the digital thread to perform data analytics, and that we can feed back into that thread to optimize our value stream. So looking on the right-hand side, you may not know it, but we do have over 70,000 AM parts on flying Boeing products. We've been involved in additive manufacturing for several decades. We began in polymer, and now we're very heavily committed to metal as well. And so these parts are in commercial aircraft, defense platforms, vertical lift, and satellites. And this chart now describes a little more of our capabilities in-house. We have this powder bed metal printing, which we see on the left-hand side. And we also have, have a lot of tie wire commitments, which we work with a supplier. And you may know there's a publicized galley fitting that's in every 787 Dreamliner. That's tie wire. We also have a lot of polymer printing, and what's shown there is the large-scale additive manufacturing printer. It can print parts, polymer parts, tens of meters long, typically tools for large things like wings. There's a lot of polymer printing capability and fused FFF or fused filament fabrication, as you see, and the whole post-processing value stream. And the materials are shown below. We're focused on titanium and aluminum, high-strength aluminum. We're onboarding steel and Inconel, and the others are the polymer that are in the work. Okay, so this is our metallic timeline. I'd like to, really point out that our AM timeline, spans about 2 decades before this, beginning with polymers. But this is when we first, we're looking, when we first inserted metal, and it began in 2001 with the X37A tie wire part, as you can see there. Then in 2003, 15 replacements aircraft on that 15 for pylon ribs, C-17, and so forth. And more recently, 2016 began our first powder bed parts. And what's shown there is an E-beam titanium powder bed part. 2017, we see that Dreamliner production part. That's a tie wire. And not shown here, but something that I will discuss in this talk is, another component, which is around 2017 and 18, a bracket which holds an ion thruster. It's quite important on satellites, as well as this Amos 17 command horn antenna. So I'm going to discuss those two parts in this talk. And those are really, unfortunately, the only ones that I'm allowed to talk about. There are really a lot more in other products. Okay, so let's talk about industry trends. We've been really steadily maturing our AM technology and understanding over the years, and there's also been a lot of concepts in industry over the last several decades that have led to greater efficiencies in manufacturing. And the first really began with the Internet of Things, or IoT. And that is really the interconnection via the internet of sensors embedded into everyday objects. And as you know, this really began with consumer products, but later, transitioned into more industrial products. And in situ monitoring in our AM machines is an example of an IoT. And then next came Industry 4.0. And basically what happened here is that people began to understand that automation and data exchange in manufacturing ecosystems could be connected, and there's great value in that, right? So basically, we learned that we can optimize our manufacturing ecosystem by integrating them. So it's not necessarily a technology play, but really realizing the value of connected systems. And most recently, we have the digital thread. And that's been the focus of a lot of conversation. It's the framework which connects our data flows on every element of our value stream. And it allows a holistic picture of our cycle. It allows us to capture that data and to perform analytics and provide feedback, make some smart decisions, provide feedback into that value stream, and continuously optimizing that. It allows us essentially to scale and to increase our quality. So at Boeing, our additive manufacturing capabilities, or activities, I should say, are really divided into these 4 pillars that we call them of BAM. BAM is Boeing Additive Manufacturing. So we have our fabrication, and most of it is focused in Auburn, which, in Seattle. Engineering, which comes from across the entire enterprise, BCA, BDS, BGS, and it could come from our UK sites and so forth, our international sites as well, and that feeds in. The R&D work is really our lower TRL maturation activities, such as material development, new alloy development, new processes, and all of our specification development comes from there. And finally, our intelligence center, and this is the group which works on everything digital with respect to AM at Boeing. It is responsible for connecting our digital thread, for collecting the data and archiving it, for creating those data analytics, machine learning, intelligent decisions so that we can feed that back into the appropriate part of the value chain so that we can completely optimize it. And they're responsible for the encryption of our digital build files, which we send to our suppliers so that we can maintain and control that IP. So value, I'd like to discuss a little bit about the value of AM, because I know that most people think of the value of AM on a part level, which is good, and there's a lot of value there. So if we look at the lower part of this chart, you can, with AM, you can design for additive, and you can make it lighter, you can make it, faster, you can really decrease the buy-to-fly ratio, you increase the quality, decrease the weight. So there's a lot of great ways to value capture on the part level. I see this is where a lot of people are focusing. I like to focus on the next level, which is different for Boeing, differentiating vehicle design. It could be, for any other industry, differentiating product design. And that's when we can really incorporate AM in ways where you can't incorporate traditional to create a differentiating product, right? So, you're taking advantage of the fact that you can create a part that conformally fits to existing hardware and integrate that and really, get into small spaces where you can't do that traditionally. An example might be, perhaps you can make parts smaller that enable a thinner wing of an airplane, which would it would result in less drag of the airplane, which would result in less fuel being used. And that's a huge value, much more than 20% weight savings on one small part. So we like to look at how can we create differentiating vehicles, and then program value. And so program value, clearly we can accelerate the design to market. We can be involved early stage in the tooling for prototyping, enhanced customer customization, rapid response to design changes, I'm sure as you know, points of use, repairs and data as a service, and sustainable manufacturing and sustainable products. So this is, I think, really important. That's why I've highlighted it. Additive manufacturing is a sustainable, manufacturing process, right? Because we are using essentially the material that we need. We're using less material. We recycle the material that we're not used. And so that means that the whole value stream, starting with mining the raw material, converting that material into a useful material, transporting that material to where it will be printed, all of that is significantly reducing the carbon footprint. And then we're making smaller parts, which makes the vehicles have a smaller carbon footprint when they're in service. So I think that's really important, that it's, from a sustainable manufacturing viewpoint, there's a lot of value added there. Okay, challenges. All this sounds great, but we have some real challenges. For example, most additive manufacturing machines are not designed to be integrated into a production system. I understand that there's a lot of good advancements here, but today, they're not really designed that way yet. Some don't even have the basic sensors to help with monitoring, although many do now. Each machine manufacturer has different protocols, right? So this means that significant labor is required to translate the data so that it can be accessed. And also, a lot of the times the data can't even be accessed, okay? So in order for parts to be certified for flight as well, the FAA requires, and other regulatory bodies as well, that we have repeatable, reliable process across machines. And it becomes really difficult to do that if the machines are not industrialized, and each one needs to be tweaked, in order to have conforming performance. And beyond the technology, there are IP concerns that can lead to difficult contract negotiations. How do we make sure that the scan strategy is always exactly the same from build to build? And we need to ensure that the post-processing portion of the value stream is also fixed and repeatable, and that the supply chain is suitably established and healthy. So if we're going to move into serialized production, we really need to address these challenges. And this is basically how Boeing is addressing some of these challenges. It really starts with the requisite framework for this. The engineers need to learn to design for function rather than to design for traditional manufacturability. They need to erase every notion of what they think the part needs to look like and design it for what it needs to do and how it needs to, be affixed to the rest of the surrounding environment. We need to design for additive manufacturing. We need to incorporate simulations that reduce the physical build iterations and provide learnings for, successful builds. And standards are really important. If we're going to scale, we require standards and specifications. And if those can be industrial, all the better, because it really helps the suppliers, be significant contributors. It makes it easier. And Boeing is releasing 2 industrial sponsors at the end of this year. Right now, they're in, comments stage, and we would think that this will really help onboarding new suppliers. With respect to the manufacturing stream, our sensor-based technologies provide the ability to include our data-driven modeling results feedback into our work stream, optimizing our flow. Everything within our flow must adhere to fixed process. It's sort of my mantra. If there's a lapse in quality, it's because we have had a lapse in fixed process. We haven't adhered to that fixed process. And finally, post-processing. This is often very overlooked, but it's very important, and it's got to be automated with scalable solutions. So we can move away from a lot of these brute force operations. And I've been, in the rooms where people are removing powder and support structures, and they're literally brute force operations. And it requires artistry from highly skilled labor, and it's not scalable, and it's not repeatable either. So that really needs to be automated. So this is another chart essentially depicting our value stream for additive manufacturing at Boeing. And so, we have additive manufacturing parts in all types of vehicles. Examples of them are shown in the corners of this chart: civil aircraft, rockets, drones, satellites. And each one of these is, governed by a different regulatory body. And we need to adhere to the regulations of each, clearly. But regardless, they all follow the same process flow, starting with specifications and ending with quality testing and inspection. Now, what goes in each of those bubbles depends on the function of the vehicle as well as the regulatory body. But once that's specified, it's it remains fixed, and it doesn't change in order to maintain good quality, repeatable quality. This is another chart depicting our AM value chain, and I've drawn the little sinusoidal graph above it just to kind of depict how we start weaving all of this data into our digital thread, beginning with the raw material, making sure that it conforms to, morphology, chemistry, moisture content, everything, laser parameters, as we know, power, speed, hatch, contour, offset, upskins, downskins, all of that. Build parameters, which might be resolution of the build file, temperature, recoder information, support structures, really important in AM, oftentimes overlooked, but this is oftentimes what's going to really determine if your part will be successfully built or not. The actual AM fabrication, powder removal, heat treatment, subsequent post-processes, inspection, and component testing, all of those need to be fixed and traceable and repeatable. And so, whether it be that the thermocouple is always at the exact same place during heat treatment or whatever, it really needs to be fixed, traceable, and repeatable. And so we are leveraging a lot of simulations at Boeing, and it's really difficult just to sort of, describe to you everything that we're doing. So I thought I would just talk this slide. And so basically, as you know, the AM process is very difficult to simulate. It's very challenging. It has complicated physics with length scales that vary from fractions of microns to meters, and time scales that vary from fractions of seconds to days, right? So it's complicated to simulate, and so there are often many different simulation paths. In addition, the development of data-driven models using advanced analytic methods such as AI and machine learning can be used to develop new predictive models as well. So what physics is actually modeled? So we have several scales: microscale, mesoscale, and macroscale modeling going on at Boeing. We simulate the fundamental melting and cooling of the AM process, such as the interaction between the heat source and the feedstock material, predicting the size of the melt pool, and attempting to understand the characteristics of that heat-affected zone. We then simulate the solidified materials composition and microstructure to predict the material performance. And finally, on the macro scale, the deformation of the part, trying to understand any potential process errors that we can mitigate. And we put this all together in our digital thread. So this is our end-to-end digital thread, starting with concept, ending with monitoring and service. And in each of these buckets of our digital thread, we are creating, generating, and collecting data that we archive. And in that archival, then we have our data analytics, where we are creating our models, data-driven modeling. And that's, as you can see in the green lines, they go back, and feedback will go back to optimize our overall value chain. And once that's optimized for a specific part, that's fixed, and then we are producing that. So this is ongoing at Boeing. We find it extremely important. A lot of this is all distributed, right? It doesn't need to be in the same place. Some of these items occur, at suppliers, and some at Boeing, and we're connecting it all through the digital thread. So we put it all together. I'm going to show you two examples that I'm allowed to show you where we have parts in flight right now on products using aluminum powder bed technology. So the first is a mission critical deployable ion engine mount, which was most recently launched in December of 2019, but that wasn't its first launch. The entire component consists of 3 assembled pieces. You can see in that center figure, and end to end, that's a little over 1 meter, I would say, in size. And to get an idea of the part size, the Y on the left-hand side, we call that the upper Y. It was created in an EOS M400 machine on an angle, so a little over 16 inches long. And it's an important part. Clearly, it is holding on. It is basically holding the engine, ion engine mounts. So let's see. So they're standard now. This component is standard in every Boeing 702 MP-derived spacecraft with xenon ion propulsion. And the assembly resulted in a 28-pound weight reduction over the Heritage composite assembly. And that lower image was taken as it was deployed in space. And the second part I want to show you is the command horn satellite antenna, which was launched on the Amos 17 satellite. You can see the original Heritage design is on the left-hand side, pink tones, and it has many different components that are bolted together, screwed together. There's an internal aperture, which was hand-tuned with a little set screw. It's a complicated little piece. The AM part is shown on the, in the center of the figure. It's a monolithic part. It didn't require any support structures, which means that we're not messing with the surface to make it more robust. The tuning was accomplished in the design phase, so there's no little set screw. We can see that on the right-hand side, it went through a really rigorous testing program of mechanical and thermal analysis, environmental testing, and performance testing. And this is basically the mission critical part. It's very small, but it was very important. It powered up the electronics of the spacecraft and also assisted in orbit transfer. So it was a critical part. The AM part resulted in a 57% part reduction and a 90% cost reduction. And I'd like to call your attention to the picture. This is the happy team that was involved in its testing. And I really want to point out Nicole, who would be embarrassed if she knew I was doing this, is on the lower right. She was responsible for the entire project, from the structural design, the AM design, the thermal, mechanical, electrical, environmental analysis, and the thermal, mechanical, environmental, and electrical and performance testing. She did everything. There was no throwing it over the fence to the next person. And she did this all only 2 years out of college. So we really look for those opportunities to mentor young students. You know, she is now our prime, powder bed antenna designer. And we really take pride in these mentorships, as well as looking for places where we can really increase the diversity in our teams, because that's really important to our mission. So I would like to, this is one more slide, I forgot. This is basically the part on the spacecraft and as it's being launched on the SpaceX Falcon 9 in 2019. And it's nicely orbiting, serving its purpose as it's intended. And finally, I like this quote. It's from Heraclitus, and the actual quote is in Greek, "ta panderi," which is translated as "it always flows." But a translation that I like that has been attributed to him also is, "Nothing ever is. Everything is in a state of becoming." And that's what I think of with additive right now. I mean, we're continuously evolving, we're continuously getting better, we're continuously improving, we're continuously becoming. And so I would like to close with that. Tapandari. Thank you. And I will stop sharing.
Yeah, thank you so much for that incredible presentation. And I loved the way that you ended with the part that additive manufacturing is a journey. So thank you so much for sharing some of the Boeing journey with us. We do have time for a couple questions. So I will go over to the Q&A tab, them that have gotten some votes. The first question is, what are some of your biggest challenges when inspecting AM production parts?
Okay, so first of all, a challenge would be if the part was not designed for inspectability clearly, right? So what you want to do in the design phase early on, is really make sure that it is designed for not just additive manufacturing with respect to, powder removal and things like that, but also for inspectability, to make sure that you can, CT scan it, that you can get a probe in there with a Orme or arm. So we do see challenges where people really take some, a conventional part and they just swap it over to AM, which is never a smart thing to do. And that's where we see the challenges. But if it's well thought out, we always say, don't just design for manufacturability, but you have to consider everything that part will experience in its life, from, the testing as well. Make sure that you can put an accelerometer somewhere on it, to making sure you can hold it in a fixture, and making sure that you can inspect it. So we try to tackle that early on, rather than scrambling to figure out what to do, with the wrong sort of design. But we rely a lot on CT scanning, and I know that there's some that if you're using titanium and they're quite thick, it might be difficult. So those kind of parts are challenging, and that's why we really like to address it in the design phase.
Okay, great. Well, thank you so much.